So now let's see one example where the previous one only, the number could even contain decimal point 11.01 like this, something like this. So we know how to find out the value of a binary number into decimal. We have converted it. But then when we have any decimal point, then this is a different case. So there are various ways. So what is the weight of this one? If I have something like dot 1101, weight of this one is 2 power minus 1, weight of this one is 2 power minus 2, weight of this one is 2 power minus 3, weight of this one is 2 power minus 4, right? And you could multiply and then add them and we are going to get the final answer. But this method could work in general, but then if you have a grammar and then if we are trying to convert it using SDT, it is better to use some other method. Other method is, if I have some value like this 0 1, what is the value of it is, how to get it is, assume that there is no decimal point here. Let us say there is decimal point followed by 0 1. Assume that there is no decimal point here. Then what is the value of this value of this binary number in decimal? Value of this binary number in decimal is simply 1. 1 upon, count the number of bits. How many bits are there? How many bits are there? 2 bits, right? Therefore 2 power 2, which is nothing but 1 upon 4, which is 0.25. So that is one other way to evaluate it. For example, if I have 0.11, what is the value of it is? Find out what is the decimal value of this number without using having assume that there is decimal point. So what is the decimal value of this 11? It is 3 upon 2 by, how many bits are there after dot? There are 2 bits, which means 2 by 2 square, which is nothing but 3 by 4. So that is nothing but 0.75. So we are going to apply this method. What is the method? We are going to count the number of bits after decimal point, and then we are going to evaluate the number as if there is no decimal point, and then we are going to divide the number by decimal value upon 2 power number of digits. Therefore, if I have to generate all the numbers, binary numbers with a decimal point, then the grammar is, there is a slight difference in the grammar. Grammar is going to look like this. A number, decimal number is going to be a list of bits followed by a dot followed by a list of bits. So this is nothing but the decimal point, the radix point, and the number could be 11.01. 11 is first list and 01 is second list. Just to differentiate first list from second list, I am going to write 1 and 2. Both the lists are same, both the L's are same. Just to differentiate it, I am writing it like this. Okay, and the remaining grammar is simple. A list can be either a list followed by a bit or simply a bit, and a bit can be either a 0 or 1. And the grammar is, this is the grammar, and now SDT is going to be straightforward. Let me take the SDT. SDT for this is, first thing is, you have to find out the decimal value as well as the number of bits. You have to count both of them. Therefore, if the production is b derives 1, then what is the decimal value of that b as well as what is the number of bits? So b dot count is used to count the number of bits. There is only 1 bit, therefore count is 1, as well as b dot decimal value. B dot decimal value, if there is only 1, is simply 1. And if b derives 0, in this case also b dot count equal to 0 and b dot decimal value equal to 0. Sorry, b dot count equal to 1. Why? Because there is 1 bit, na? Okay. And this one, if list is simply 1 bit, then list dot count is directly 1 bit. You can write it, or you can either write it as bit dot count. Okay, because anyways bit dot count is going to be 1, and L dot decimal value equal to whatever was the b's decimal value, that we are going to write it here. Okay, and now there are two L's. One L is on the left side and one L is on the right side. Just to differentiate between these two L's, I am going to make the suffix 1, L1. It doesn't mean that L1 is different. Now if I have a list as list followed by a bit, then number of bits in the list is equal to number of bits in the list plus number of bits in that bit. This is the total number of count as well as Now L dot decimal value, what is the decimal value of L is L1 dot decimal value plus B dot decimal value. Okay, and now coming to this number, now the number's value is whatever is L1's decimal value, we have to write that one, and coming to L2's decimal value, you have to take the L2's decimal value and then divide it with L2's count, which means if I have to get the total number of the total value of n, then it is going to be, first thing is you have to find out L1's decimal value. What is L1's decimal value? That is already given, that one we have already derived it till here. So L dot decimal value we have derived it, therefore number dot decimal value is equal to, can write like this, the final decimal value of the number is whatever is the decimal value of L1, which means L1 dot decimal value plus whatever is the decimal value of L2, L2 dot decimal value divided by 2 power L2 dot count. The reason is this number is going to be the fractional part which is equivalent to L2, and this number is going to be the decimal part which is equivalent to L1. That is how we get it. So if you want to see an example, let us say the number is L1 11.01, then we are going to evaluate the decimal value of this, which is nothing but 3, plus we are going to evaluate decimal value of this, which is nothing but 1, divided by 2 power number of bits. What is 2 power number of bits? 2 power 2, which is nothing but 3 plus 1 by 4, which means 0.25, which is 3.25. So that is how this SDT is going to work. So this is an SDT to convert any binary number, including binary numbers containing decimal point, into decimal number. Okay, so we shall see next example. This is an SDT to generate 3 address code. So what is 3 address code is, it is an intermediate representation. For example, if I have something like this, if I have x equal to a plus b into c, this is actually containing 4 addresses. So I want to convert this 4 address code into 3 address code. For that we are going to use something like this SDT. So if you look at this SDT, we have few things here. See, first thing is the grammar is nothing but a statement can be identifier equal to expression, and an expression is expression plus term or term, and a term is term into factor or factor, factor is id. So this is actually supposed to generate all the statements of the form x equal to a plus b into c, right? And now in order to generate it, see this, we are going to use this entire semantic rules. So semantic rules are this: f dot place is an attribute which is used as a placeholder, which means it is going to remember what is the name of that variable. For example, here id can be a, b or c, right? In that case, then it is going to be f dot placeholder equal to a or b or c, something like this, and then t dot place equal to f dot place, and then t dot place equal to new temporary variable, which means sometimes we are going to create a new temporary variable, and then to that temporary variable we are going to generate this code. This gen is nothing but the output. So because of this piece of code, we are going to write output, in the output the 3 address code required. It is better I'll take an example and I'll explain you. See, let us assume that this is the example for which I want to generate 3 address code. Okay, now for that one I am going to construct the tree. A statement can be identifier equal to expression, and the expression can be expression plus term, and term can be term into factor, and a factor can be simply an identifier, and a term can be a factor, term can be a factor, and factor can be an identifier, and expression can be term can be factor can be identifier. Okay, and now this id is nothing but a, and this id is nothing but x equal to a plus b into c. Now let me do bottom up parsing. This is not a reduction, this is not a reduction, this is a reduction. So what is reduction? ID is reduced to f. When ID is reduced to f, what is the action associated with this? F dot place equal to id dot name. What is id dot name here? Here id dot name is nothing but a, which means f is going to remember that the variable it has seen is a, and again there is a reduction. So what is reduction? F is reduced to t. F is reduced to t. What is the action? T dot place equal to f dot place, which means t dot place equal to whatever was f dot place, which is a. Okay, and now t is reduced to e. T is reduced to e. Then what is the action? E dot place equal to t dot place, which means e dot place equal to t dot place is nothing but a. This is not a reduction, and again this is a reduction, right? ID is reduced to f. ID is reduced to f. Then what is the action? F dot place equal to id dot name, which means f dot place equal to, what is id dot name here? B. And again this is a reduction. F is reduced to t. F is reduced to t. What is the action? T dot place equal to f dot place, which means t dot place equal to f dot place is nothing but b. This is not a reduction. And again this is a reduction. ID is reduced to f. What is the action? F dot place equal to id dot name, which means f dot place here is nothing but c. So all the variable names have been remembered till now. Now this is again a reduction. What is reduction? T star f is reduced to t. T star f is reduced to t. In that case, what is the action? One action is t dot place equal to new temporary variable, which means for the left side t, see, left side t is t and right side t is t1, which means for the left side t we are going to create a new temporary variable. Let us say new temporary variable is t1. So t dot place equal to, I created a new temporary variable t1, and now I am generating the code t dot place equal to t1 dot place into f dot place, which means t dot place, which is nothing but t1, is equal to t1 dot place, which is nothing but b into c. So because of this reduction, output is going to be printed as t1 equal to b into c, which means for this input the output started as t1 equal to b into c, which means this is evaluated first, this part, right? And again there is a reduction. What is the reduction? E plus t is reduced to e. E plus t is reduced to e. Then what is the action? E dot place equal to new temporary variable, which means for this e we are going to create a new temporary variable. So e dot place equal to new temporary variable, let us say t2, yes, and now generate e dot place equal to e1 dot place plus t dot place, which means e1 dot place t2 equal to e dot place, which is a, plus t dot place, which is t1, which means t2 equal to a plus t1. See, for this one we evaluated it as t1, and now we added these two and we evaluated it as t2, right? And now again there is a reduction. What is the reduction? ID equal to expression is reduced to s. ID equal to expression is reduced to x. Then what is the action? Action is id dot name is equal to e dot place. Then what is id dot name here? Id dot name is nothing but x. X equal to e dot place. E dot place is nothing but t2. Therefore, for this input, which is containing 4 addresses, we have converted into output in which every line is containing maximum of 3 addresses. Therefore, this is the SDT which is used to convert any input program into 3 address code, which is following this grammar. So in general, if the program is containing if else and all and other statements, then we have to write the grammar for all the statements possible, and then we have to write the rules for all the statements. Okay, and this is how we converted the input into output. We shall see more examples. Now we have seen many SDTs till now. Now we can classify SDTs into 2 types. One is S attributed SDT and other is L attributed SDT. So before going to classification of SDTs, I want to classify attributes first. So till now we have seen that every variable is having an attribute associated with this, and it is getting some value, right? And there are two ways. So one is, if I have a production like this, just for an example, see this, A derives B, C, D, something like this. A can have an attribute, which means A dot S. A can have an attribute, and if it is getting the attribute as a function of attribute of B, attribute of C, and attribute of D, which means A is taking value from its children. In case if A's attribute is taking value from its children, then such an attribute is called synthesized attribute. Why? Because we are synthesizing the value of the attribute from the children. And other way is, if let us say C is taking attribute from its parent or from its siblings, then such an attribute is called inherited attribute, which means if I have C dot I is an attribute, and if it is taking a value from A dot I, something like this, which means a child is taking a value from parent, then it is called inherited. Or C dot I, if it is taking a value from B dot I, which means a node is taking a value from its sibling, or C dot I is taking a value from D dot I. So if a node takes the value from its parent or from its siblings, then it is called inherited attribute, and if a node takes a value from its children, then it is called synthesized attribute. Therefore, attributes are basically of two types. One is synthesized and other is inherited. What is synthesized? If a node takes the value from its children, then it is called synthesized, and if a node takes a value from the parent or from its siblings, then it is called inherited. So depending on what are the types of attributes you have in SDT, SDTs can be classified again into two types. We shall talk about SDTs first. You know what an SDT is, we have seen it till now. Now in all the SDTs we have seen till now, we are having some attributes and we are trying to evaluate the values of the attributes. So I'll tell you an example. S attribute at SDT is nothing but, in an SDT, if there are only synthesized attributes, which means a parent is taking the value from its children. If there are only synthesized attributes, then it is called S attributed definition. And L attributed definition is, it can have both inherited attributes as well as synthesized attributes, but only restriction is we should inherit from the left side. That is why it is also called as L attribute. See this, it is going to have both inherited as well as synthesized, and in case of inheritance, you are not supposed to inherit from your right side, you are supposed to inherit from your left side only. That is why it is called L attributed definition. In this case, see this, A derives x, y, z. In this case, x can take value from A, y can take value from x, but y cannot take value from z. See this, y can take value from A, y it can take it from the left hand side, yes, this is allowed. And then y can take value from x, y because it is taking from left hand side, it is allowed, but then y cannot take value from z. The reason is, y can take only from its left hand side, which is A or x, but it cannot take from right hand side, okay. And moreover, A can take value from x, y, z, because that is nothing but synthesized attribute. So in L attributed definition, we have a combination of S attributed as well as inherited attribute, synthesized as well as inherited, but inheritance should be only from the left hand side. So which one do you think is powerful? S attribute is taking only synthesized, L attribute is taking both synthesized as well as inherited. Therefore this is actually, L attributed definition is actually enclosing S attributed definitions also. If a definition is S attributed, then it is definitely L attributed. Why? Because L attributed can allow both synthesized as well as inherited attributes. Now coming to the second rule, the semantic actions are always placed at the right end of the production, which means here if you are going to place some semantic actions, you should place them only in the right side, right end, at the rightmost. But here, coming to L attributed definition, semantic actions can be placed anywhere in the right hand side, which means you can place it in the beginning or in the middle or in the end, right? Even by this definition, S attributed is more restricted, but L attributed is more free, right? And if you see this, since we are placing the semantic rules only in the right hand side of the production, it is also called as postfix SDT. Postfix means we are going to have the semantic rules at the end. Post means at the end. And next one is, attributes are evaluated during bottom up parsing. So since it is all synthesized attributes, when we come from the bottom, which means let us say like this, since A's values depend on B, C, D, so by doing this bottom up parsing, by the time I reach A, I will have scanned all the children. That is why it is easier to evaluate during bottom up. Here attributes are evaluated by traversing the parse tree depth first, left to right. The reason is, see this, if I have something like this, A derives B, C, D, then C could take values from A and from B, but it will not take value from D. Therefore, if I am traversing from top down, left to right, by the time I reach a variable, all the values of the left side are already available. Values at A and B are available, using which I can evaluate the value at C. So understand this. Here values are evaluated in a bottom up parsing. The reason is, by the time I reach, by doing this bottom up parsing, by the I could see all the values that A is depending upon first, and then I can come here. And similarly here, attributes are evaluated by traversing the parse tree depth first, left to right. By the time I reach any variable, all the parents have been watched and all the left subtrees have been watched. Therefore, by the time I reach here, all the values that C is depending on are already being evaluated. Okay. So this is the main difference between S attributed and L attributed. I'll take an example and I'll give you, more insight about this. Yeah, see some examples. In this example, I want to show you whether how to find out whether a SDT is L attributed or S attributed. Okay. So first of all, see this first SDT. There are two productions and there are some associated semantic actions with this. Okay, you can have a look at that. Now the question is whether this SDT, both the productions together is called SDT. Okay, both these productions along with these rules is called SDT. Whether this SDT is S attributed, L attributed, both or none. That is what is the question. Now examine each variable, each attribute one by one. Then you can find out. So first one is L dot I equal to F of A dot I. So what does it mean? L is taking value from A. So child is taking a value from parent, which means this L dot I is nothing but inherited attribute. So since it is inherited attribute, this SDT cannot be S attributed. Why? In S attributed SDT, there has to be only synthesized attributes. Therefore, because of this rule, there could be some other rules also which are failing, but then just because of this rule you can stop here and you can say that this is not S attributed definition. Okay, and now let's check whether it is L attributed definition or not. L attributed definition means, see, you have to take only from your left hand side, which means L can take from A, yes, it is fine, and M is taking from L, yes, N can take from L, it is fine, and A is taking from M. A is taking from M. Just check this. How could A take from M? Yes, it could take it. The reason is you are taking a value from your child. It is nothing but synthesized attribute. Therefore, these two rules are according to L attributed definition, right? And now see this. Next one, R is taking from A. R is taking from A. Yes, it could take it. So any variable on right hand side can take anything from left hand side, right? It is inherited, fine. Now Q is taking from R. Q is taking from R. That is what it should not happen. You should never take any value from your right side sibling. If it is happening, then it means that it is not L attributed definition, which means because of this it is not L attributed definition. So remember this, if I have any production A derives B, C, D, now in S attributed definition, A can take from B, C, D, that is fine. In L attributed definition, A can take from B, C, D, and B can take value from A, and C can take value from AB, D can take value from ABC. But then C cannot take value from D, or B cannot take value from CD. If you see any such rules, you can say that it is not L. Therefore, because of this rule, this rule, it is not S attributed, and because of this rule it is not L attributed. We can say that it is none, not S attributed or L attributed. Now let's look at the next production, A derives BC. So in this production, the action is, the action given is B dot S equal to A dot S, which means B is taking a value from A. So B is inheriting a value from A. It is an inherited attribute. Yes, inheritance is allowed, right? And moreover, we are taking inheritance from parent, which means left hand side. Therefore, it is not a problem. So this is L attributed. It is not S attributed because it is having inheritance, right? Inherited attributes does not form S attributed definition. And one thing you should even observe is, if an SDT is S attributed, then it is definitely L attributed. The reason is this: in S attributed, see, if a grammar is S attributed, then definitely it is, if an SDT is S attributed, then definitely it is L attributed. The reason is this: the reason is, if a SDT is S attributed, you can understand that there are only synthesized attributes in it, and since there are synthesized attributes, it is definitely L attributed. But if a grammar is L attributed, there could be synthesized as well as inherited attributes. Therefore, if a grammar is L attributed, it may not be S attributed. It may or may not be. Okay. So now this is an example. We shall see one more example, and I will show you the difference between S attributed and L attributed.